Hello, my friends. Welcome to Thermal Engineering Concept and Principle. How can we determine the dimensions of geothermal vertical heat exchangers? This is the objective of the present episode. Come with me and let us go deeply in this subject with Professor Ali Tarad. Dear friend and colleague, welcome again to your channel and let us continue in presenting the thermal design of the borehole heat exchanger, which is integrated with the heat pumps. In this part, we will talk about the analytical modeling technique, which was used in presenting the heat exchanger and to predict its overall thermal resistance and the depth of the heat exchanger. I would like to thank you for your continuous support to the channel and sharing it with others to get the best output of our effort. The objectives of the present episode is related to presenting a practical application for the geothermal heat exchangers, which are integrated with the geothermal heat pumps for heating or cooling systems. And we will pass through W tube heat exchanger application, where the theoretical part has been explained and discussed in the previous episode. The the model which we will talk about and its application for the W tube is similar to that used for a single U tube in this part. Therefore, we will go through the application of the W tube, and you may use it for the single U tube application. And then we will arrive to the closure. We take an industrial case study where a geothermal heat pump is used and it utilizes a direct or DX heat exchanger, which acts as a condenser heat exchanger, geothermal type, and we have Freon R410A refrigerant, which is circulated in this system with a condensation heat transfer coefficient of 3000 watt per meter squared degree centigrade is used as a typical value. We will apply a double U tube made of copper, and both the descending and ascending sides of the tube are having the same diameter with different geometries as shown in this table, with WF represents the tube wall factor, which can be obtained by dividing the outside diameter by the thickness of the tube, and we have T is the thickness of the tube, of course. And let us find the performance of the W tube for these geometries with a range of thermal conductivity of the grout material ranged between 0.73 watt per meter Kelvin up to 1.9 watt per meter Kelvin as shown in the table, and these materials are well known to be utilized in this type of heat exchangers, and some of them are mixture between different materials such as bentonite and 30% quartz. So it's a range of these materials can be used just to improve the thermal conductivity of the crude material, which is reflected on the performance of the tube itself. To compare the borehole thermal design, and we will focus on the thermal resistance of the tube. For example, here we have geometry factor SP divided by dB equal to 0.34 up to 0.56, and these values of SP divided by d-bore, which is representing the geometry factor, are obtained for a constant borehole diameter. In this figure, we may see that all these values, regardless of the geometry factor, behave on the same manner. We have a maximum at 0.73, and the minimum will arrive at the value of 1.9. And as we increase the geometry factor from 0.34 to 0.56, the thermal resistance is reduced by tremendous value, and of course that will be reflected on the heat loading of the heat exchanger and the thermal performance of the heat pump itself. And the lower value was obtained for geometry factor equal to 0.56 because in this case we have a constant borehole diameter, but the distance between these two legs of the tube are increased, and in that way we are minimizing the distance between the borehole surface, external surface, and the surface of the tube, and the distance is reduced, therefore the thermal resistance will be reduced as well. We have the same behavior when we have WF equal 12.5, and again here the thermal resistance are higher than the previous one, and again we have the same behavior from a maximum value at 0.73, which corresponds to around 0.3, down to 0.16 for the same thermal conductivity, and is reduced to a value of around 0.12 for the geometry factor of 0.29, and it's reduced to a minimum for the geometry factor of 0.59 at a value almost correspond to 0.06, and we can see the difference almost double. Now let us see the effect of tube spacing on the thermal performance. For example, here we have WF equal 14.29 for different values of SP range between 2 D node up to 3 D node for both geometries of the single tube and double U tube as compared here in this figure. And the single tube at the same SP, when it is compared to the double tube, usually the single tube has a higher value than that of the double tube. For example, if we use a form that is eta equal r bore when we have 2 d naught sp equal to 2 d naught minus r, and where we have sp equal to 3 d naught divided by r sub b, where we have sp equal to d 2 d naught. Here, for this geometry, the lower tube spacing to denote exhibited a higher thermal resistance than that of the 3D node in the range of 22 to 24% for the single U-tube, and it fell in the range of 32 to 34% for the double U-tube case, where we have the same variation of SP between 2D note and 3D note. Again, if we compare the borehole resistance for the single and the double U-tube as represented by zeta, we have the value of zeta fell in the range between 14 to 16% and 25 to 27% predicted as the tube spacing of 2D note and 3D note respectively. And that means usually we have the enhancement or the performance or the different depend on the SP value. And this is the case for the WF equal to 14.29. Of course, we have the single tube at SP equal to D naught has the higher value and approaches around 0.3 at 0.73 watt per meter Kelvin, and falls down to around 0.14 for thermal conductivity of the root corresponding to 1.9, and the lower value was for the double U-tube for SP equal to 3D naught, and here almost is double, as we can see from this figure. And if we talk about 12 WF equals 12.5, we have the same variation, that is usually when SP equal to D naught is higher than that of 3D naught for both geometries, the single and double U-tube. And at the same time we have zeta is having the same values. I mean, we have the single U-tube is higher than the double U-tube for the borehole thermal resistance. And here we have eta for this geometry is range between 18 and 19% for the single U-tube, and it is range between 22 to 23% for the double U-tube when we have the tube spacing was 2D naught and 3D naught respectively. At the same time, we have zeta for this geometry fell in the range between 10 to 11% and 15 to 16% for the tube spacing 2D naught and 3D naught. Of course, these values depend on the tube spacing. I mean, for the borehole resistance for both tubes, single and double U-tube. And wherever we have the tubes are close to the boundary of the borehole, then we will get the lower value of borehole thermal resistance, and usually the single U-tube showed higher borehole thermal resistance than that of the double U-tube. Let us compare what we have in the present video and the present correlation with the available correlations. Of course, there are not too many correlations available in the open literature for the W-tube, but we may compare the present model with two of them, that is Schonder and Beck, and the other is the Koenig correlation. Both of them represent the higher and lower values, of course, although the higher value in this model is showed by the present work or the present correlation, but again, it's very close to Schonder. And we have to mention here that Schonder and Beck correlation doesn't depend on the borehole diameter and the spacing between the tubes. But the other correlations, I mean the present model and the Koenig equation, represents variation and showed its influence by the change of these values of SP and DB. And all of these correlations show the same behavior and the trend of these thermal resistances, and Koenig model showed a very low values when we compare them with the present and Schonder and Beck correlation. Here we have the WF equal to 12.5, where we have the DB equal 65 millimeter. Again, we have here Schonder and the present model showed the higher value, and they are very close to each other, and the minimum value was obtained by Koenig equation, and the present correlation and Koenig correlation showed variation depending on the value of a geometry factor, which is SP divided by dBor. For example, at 0.29, we have the higher value of the thermal resistance, where the a lower value was obtained at SP divided by dBor equals to 0.48, which is represented by the blue line, and these values show that the higher the thermal conductivity of the grout material, the lower thermal resistance, which is reflected, of course, on the size of the tube and its depth. Therefore, we have to select an accurate correlation to predict the thermal design of such heat exchangers, as can be seen here that, for example, for the present model and Schonder for geometry factor of 0.29, almost the thermal conductivity at thermal conductivity of 0.73, the thermal resistance around to 0.28. When we compare at the same value with the Koenig equation, almost is 0.1. And we can see here that the difference will be huge in the thermal design for the depth and the surface area of the heat exchanger, as it's varied from a little value at 0.1 up to a high value at 0.3 for the thermal resistance. And again, if we increase the thermal conductivity to 1.9, then we will get the best performance for all of these relations and predict a lower value for the depth or the length of the heat exchanger itself. Dear friends and colleagues, we have arrived to the closure of the present episode where we have used the application of the W tube in geothermal heat exchangers, and the analytical modeling was applied. Of course, this procedure can be used for the single YouTube as well. There are some references where can we make an advantage of them in the description box below this video. Thank you for watching and listening, and I hope that you will share this video with your colleagues and friends. See you in the next uh, episode in the field of thermal engineering. Bye bye.